Hello friends, till now in our discussion on rotating bodies we have been talking about rotational variables, kinetic energy of rotation and rolling, rotational inertia and torque. The central topic of today's lecture is going to be angular momentum, a quantity that plays a key role in rotational dynamics. In analogy to the principle of conservation of linear momentum, there is also a principle of conservation of angular momentum. The angular momentum of an isolated system is constant. For angular momentum, an isolated system is one for which no external torque acts on the system. If a net external torque acts on a system, it is non-isolated. Like the law of conservation of linear momentum, the law of conservation of angular momentum is a fundamental law of physics. Angular momentum. Figure shows a particle of mass m with linear momentum as it passes through point A in an xy plane. The angular momentum of this particle with respect to the origin O is a vector quantity defined as L is equal to r into p and is equal to m into r into v. Here r is the position vector of the particle with respect to O. As the particle moves relative to O in the direction of its momentum, position vector r rotates around O. Note carefully that to have angular momentum about O, the particle does not itself have to rotate around O. Now, we shall compare the torque equation tau is equal to r into F with angular momentum equation, and we find that angular momentum bears the same relation to linear momentum that torque does to force. The SI unit of angular momentum is the kilogram meter squared per second, equivalent to the joule second. To find the direction of the angular momentum vector L in figure, we slide the vector p until its tail is at the origin O. Then we use the right hand rule for vector products, sweeping the fingers from r into p. The outstretched thumb then shows that the direction of L is in the positive direction of the z axis. This positive direction is consistent with the counterclockwise rotation of positive vector r about the z axis as the particle moves. The angular momentum of a system of particles. Now we turn our attention to the angular momentum of a system of particles with respect to an origin. The total angular momentum of the system is the vector sum of the angular momentum of the individual particles, that is L is equal to L1 plus L2 plus L3 and so on up to Ln, and this is equivalent to sigma Li from I is equal to 1 to n. With time, the angular momentum of individual particles may change because of interactions between the particles or with the outside. We can find the resulting change in the vector L by taking the time derivative of this equation. Thus, dl upon dt is equal to sigma dli upon dt from I is equal to 1 to n. Here we see that dli upon dt is the net torque T net on the ith particle. So, we can write dl upon dt is equal to sigma tau net I from I is equal to 1 to n. That is, the rate of change of the system's angular momentum is equal to the vector sum of the torques on the individual particles. Those torques include internal torques due to force between the particles and external torques due to forces on the particles from bodies external to the system. However, the forces between the particles always come in third law force pairs, so their torques sum to 0. Thus, the only torques that can change the total angular momentum of the system are the external torques acting on the system. Now, let tau net represent the net external torque, the vector sum of all external torques on all particles in the system. Then we can write the above equation as tau net is equal to dl upon dt. This is Newton's second law in angular form. It says that the net external torque acting on a system of particles is equal to the time rate of change of the system's total angular momentum. The Newton's second law equation in angular form is analogous to F net is equal to dP upon dt, but requires extra caution. Torques and the system's angular momentum must be measured relative to the same origin. If the center of mass of the system is not accelerating relative to an inertial frame, that origin can be any point. However, if it is accelerating, then it must be the origin. For example, consider a wheel as a system of particles. If it is rotating about an axis that is fixed relative to the ground, then the origin for applying this equation can be any point that is stationary relative to the ground. However, if it is rotating about an axis that is accelerating, such as when it rolls down a ramp, then the origin can be only at its center of mass. The angular momentum of a rigid body rotating about a fixed axis. We now evaluate the angular momentum of a system of particles that form a rigid body that rotates about a fixed axis. The fixed axis of rotation is a z axis, and the body rotates about it with constant angular speed omega. We wish to find the angular momentum of the body about this axis. We can do this by summing the z components of the angular momentum of the mass elements in the body. As in figure, a typical mass element of mass delta mi moves around the z axis in a circular path. The position of the mass element is located relative to the origin O by position vector Ri. The radius of the mass element's circular path is the perpendicular distance r perpendicular I between the element and the z axis. The magnitude of the angular momentum of mass element with respect to O is given by Li is equal to Ri Pi sin 90 degrees and is equal to Ri delta Mi into Vi. Here Pi and Vi are the linear momentum and linear speed of the mass element, and 90 degrees is the angle between Ri and Pi. The angular momentum vector Li for the mass element is shown in this figure here. Its direction must be perpendicular to those of Ri and Pi. But here we are interested in the component of Li that is parallel to the rotation axis, which is the z axis. The z component is Liz is equal to Li sin theta and is again equal to Ri sin theta into delta Mi into Vi and is equal to R perpendicular I into delta Mi Vi. The z component of the angular momentum for the rotating rigid body as a whole is found by adding up the contributions of all the mass elements that make up the body. Thus, because V is equal to omega r perpendicular, we may write Lz is equal to sigma Liz from I is equal to 1 to n, or Lz is equal to sigma delta mi vi r perpendicular I, and this is equal to sigma delta mi into omega r perpendicular I into r perpendicular I, and finally we get Lz is equal to omega into sigma delta mi into r square perpendicular I. We can remove omega from the summation here because it has the same value for all points of the rotating rigid body. The quantity sigma delta mi r square perpendicular I in equation is the rotational inertia I of the body about the fixed axis. Thus, our derived equation reduces to L is equal to I omega. We have dropped the subscript z, but we must remember that the angular momentum defined by this equation is the angular momentum about the rotation axis only. Also, I in the equation is the rotational inertia about that same axis. Conservation of angular momentum. So far, we have discussed two powerful conservation laws, the conservation of energy and the conservation of linear momentum. Now, we meet a third law of this type involving the conservation of angular momentum. We start from angular momentum equation for a system of particles, which is Newton's second law in angular form. Tau net is equal to dl upon dt. If no net external torque acts on the system, this equation becomes dl upon dt is equal to 0, or L is equal to a constant. This result, called the law of conservation of angular momentum, can also be written as net angular momentum at some initial time t I is equal to net angular momentum at some later time t f, or L I is equal to L f. These equations tell us if the net external torque acting on the system is 0, the angular momentum L of the system remains constant no matter what changes take place within the system. These two equations are vector equations. As such, they are equivalent to three component equations corresponding to the conservation of angular momentum in three mutually perpendicular directions. Depending on the torques acting on a system, the angular momentum of the system might be conserved in only one of the two directions, but not in all directions. In other words, if the component of the net external torque on a system along a certain axis is 0, then the component of the angular momentum of the system along that axis cannot change, no matter what changes take place within the system. We can apply this law to the isolated body which rotates around the z axis. Suppose that the initially rigid body somehow redistributes its mass relative to the rotation axis, changing its rotational inertia about that axis. Then the conservation law equation states that the angular momentum of the body cannot change. Substituting the value of L is equal to I omega into Li is equal to Lf, we write this conservation law as I into omega I is equal to If into omega f. Here, the subscripts refer to the value of the rotational inertia I and the angular speed omega before and after the redistribution of mass. Like the other two conservation laws that we have discussed in earlier lectures, equation for conservation of linear momentum hold beyond the limitations of Newtonian mechanics. They hold for particles whose speed approach that of light, and they remain true in the world of some atomic particles. No exceptions to the law of conservation of angular momentum have ever been found. Examples of conservation of angular momentum. The spinning volunteer. Figure shows a student seated on a stool that can rotate freely about a vertical axis. The student, who has been set into rotation at the modest initial angular speed omega I, holds two dumbbells in his outstretched hands. His angular momentum vector L lies along the vertical rotation axis, pointing upward. The instructor now asks the student to pull in his arms. This action reduces his rotational inertia from its initial value II to a smaller value If. Because he moves mass closer to the rotation axis, his rate of rotation increases markedly from Wi to Wf. The student can then slow down by extending his arms once more, moving the dumbbells outward. No net external torque acts on the system consisting of the student, stool and dumbbells. Thus, the angular momentum of that system about the rotation axis must remain constant, no matter how the student maneuvers the dumbbells. In figure A, the student's angular speed omega I is relatively low and his rotational inertia II is relatively high. According to equation II omega I is equal to If omega f, his angular speed in figure B must be greater to compensate for the decreased If. The springboard diver. Figure shows a diver doing a forward 1.5 somersault dive. As you should expect, her center of mass follows a parabolic path. She leaves the springboard with a definite angular momentum about an axis through her center of mass, represented by a vector pointing into the plane of the figure perpendicular to the screen. When she is in air, no net external torque acts on her about her center of mass, so her angular momentum about her center of mass cannot change. By pulling her arms and legs into a closed tuck position, she can considerably reduce her rotational inertia about the same axis, and thus, according to equation II omega I is equal to If omega f, considerably increases her angular speed. Pulling out of the tuck position at the end of the dive increases her rotational inertia and thus slows her rotation rate, so she can enter the water with little splash. Even in a more complicated dive involving both twisting and somersaulting, the angular momentum of the diver must be conserved in both magnitude and direction throughout the dive. Long jump. When an athlete takes off from the ground in a running long jump, the forces on the launching foot gives the athlete an angular momentum with a forward rotation around a horizontal axis. Such a rotation would not allow the jumper to land properly. In the landing, the legs should be together and extended forward at an angle so that the heels mark the sand at the greatest distance. Once airborne, the angular momentum cannot change. It is conserved because no external torque acts to change it. However, the jumper can shift most of the angular momentum to the arms by rotating them in windmill fashion. Then the body remains upright and in the proper orientation for landing. Ballet dance. A ballet performer leaps with a small twisting motion on the floor with one foot while holding the other leg perpendicular to the body. The angular speed is so small that it may not be perceptible to the audience. As the performer ascends, the outstretched leg is brought down and the other leg is brought up, with both ending up at an angle theta to the body as shown in figure B. The motion is graceful, but it also serves to increase the rotation, because bringing in the initially outstretched leg decreases the performer's rotational inertia. Since no external torque acts on the airborne performer, the angular momentum cannot change. Thus, with a decrease in rotational inertia, the angular speed must increase. When the jump is well executed, the performer seems to suddenly begins to spin and rotates 180 degrees before the initial leg orientations are reversed in preparation for the landing. Once a leg is again outstretched, the rotation seems to vanish. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt that the angular momentum of a system of particles is the vector sum of the angular momentum of the individual particles. The time rate of change of angular momentum is equal to the net external torque on the system, that is, the vector sum of the torques due to interactions of the particle of the system with particles external to the system. For a rigid body rotating about a fixed axis, the component of its angular momentum parallel to the rotation axis is L is equal to I omega. The angular momentum of a system remains constant if the net external torque acting on the system is 0. So, that is it for today. In the next lecture, we shall be talking about Kepler's laws. Thank you very much.